Welcome back. We're now up to chapter 22 in our trek through the universe. Last time we looked at the birth of stars, and now we're going to look at stars sort of from their adolescence to their old age. We will talk specifically about the death of stars more in the next few lectures. Those get very interesting when we're talking about things like planetary nebulae, which is what I've got behind me here in the backdrop, or when we start talking about the core remnants that are left over, which include white dwarfs, which is different from a brown dwarf or a red dwarf. A white dwarf is actually a leftover star or a zombie star. We'll also talk about neutron stars, pulsars, and black holes, which of course it tends to be one of the big interesting objects in terms of astronomical, stellar and galactic astronomical studies over the past couple of generations. And we'll see how that was not always the case, but we'll save those for the next few chapters. Here we're going to sort of trek through the basic life cycle of a star from after it's a protostar into being a legitimate star, an actually operating star on the main sequence of the HR diagram, through to when it begins to need to head off of the main sequence as well. So stay tuned, and let me see if I can share my screen here. Let's see, which one do I want? I want that one there. Several of them come up. We want to have the right one. So stars from adolescence to old age. There we are. You can guess which one of those I'm closer to now as well. When we look at stars, we remember we're looking at different ways in which they collapse and coalesce into actual objects of shininess. We saw how as the gases cool, they coalesce and accrete the accretion disk into something that will eventually kick on. As it loses its mass because it converts it to energy, eventually it will return to that nebular state. And one of the things that we see here is that we have the steps in stellar evolution, which represent both the end of other stars and the beginning of new stars, with this one, which is sometimes called the ant nebula, because it sort of looks like an ant. This whole thing is, again, 1.6 light years long. Again, for size comparison with our solar system, if this were 1.6 light years, our solar system would be about like that. My fingers would almost be touching in that regard. When we're looking at what's happening inside of a main sequence star, we have hydrogen being fused into helium. We will talk about that in terms of burning, although it's not chemical burning. It is a nuclear process. It is the fusion reaction process that's happening there. Hydrogen protons are being thrown together into a larger and larger construct until they become helium nuclei, which will have 2 protons and 2 neutrons. We have the proton-proton chain, which I believe we talked about in chapter 15 or 16 when we were looking at the sun. So this is what happens in the middle of a main sequence star. But eventually, we'll have a helium core begin to build up. That's the ash that's left over from this burning process. And the helium, being heavier than hydrogen, has 4 particles rather than just 1, will sink towards the bottom. But it takes a lot more energy. It takes a lot more temperature and a lot more pressure to fuse helium into higher elements. So if you're a smaller star, you never get to that point in sort of consistent way. So when we're looking at the way our sun is operating right now on hydrogen, turning hydrogen into helium, and according to E equals mc squared, releasing energy along the way. A higher mass star will have higher pressure and thus result in higher temperatures in the center. A lower mass star, our sun qualifies as a lower mass star, will have lower pressure and lower temperatures. But in the center here, they are still incredibly hot. The center of our star is going to be 10 to 15 million degrees. And we're talking about Celsius there, or 10 to 15 million Kelvin along the way. Higher core temperature has a higher fusion rate, which is why larger stars burn themselves out more quickly along the way, as we've talked about before. And I think you've seen some of the kinds of size comparisons in the video that I posted up in our class on sort of the sequence of stars and how large can get. So here we have yet another sort of way to think about things. If we were looking at this as the size of the sun, the Earth might be a very, very small pixel beside the sun here. But we can get really big and really, really, really big here. Note that this star is so large we can only see this arc portion. It has to go up. It would sort of take over half of your wall in terms of how large stars can be. Here we have main sequence stars. I think I've shown this to you before in one of the previous lectures. We see the size comparisons. Notice one mass of the sun, that's our basic unit. Sirius is 2 times that, so we call it 2m, or 2 masses of the sun. Notice the volume, how large it is, how much space it takes up, is more than twice the size of the sun. That's because the engine inside there is pumping out energy much, much hotter. There's a lot more pushing out, so it actually spreads out more. Spica up here, 11 times the solar mass, but this is much larger in volume than that. But also, again, note the timelines. The lifetime of a star that's roughly 10 times the size of our sun is actually quite small. When we get to 10 to the 7th, we're talking 10 million years rather than 10 billion years. That's a really, really, really big difference there. High mass stars have high luminosity, they're short-lived. They will tend to be on the main sequence in the blue range. We do have larger stars that are red. They have gone off the main sequence, and that's part of their sort of end stage game. Lower mass stars tend to be more reddish in color. So if you think of Roy G. Biv, up here is Biv, down here is Roy, and we're sort of in the Roy area. When we're looking again at supergiants versus us, here's our sun. If we're looking at Aldebaran, our sun would be sort of somewhere in the middle, probably not even the size of the core of Aldebaran. And when we look at Betelgeuse, again, notice this little times 5 here, this times 10, all of this. Betelgeuse would actually envelop the entire inner solar system. So the sun actually disappears in this along the way. Notice that this is much larger, but it's red. That means it's off the main sequence. It really is off the charts in many ways. So it is no longer producing hydrogen into helium. It is actually burning other things inside. It is the star up in the upper left corner. I know I've said that a couple of different times in Orion. That if there are a couple of things I hope that you'll always remember from this class. One of them is where Betelgeuse is, because again, it is the most likely star in your lifetime to explode. It's also one of the ones that's the easiest to find in the sky. Rigel is down in the corner here in the lower right, Betelgeuse in the upper left. If you're looking at the 3 stars in the belt of Orion as being roughly horizontal. So of course, Orion's going to shift in the sky as you're sort of watching it go through the night sky. Here we can see size comparisons for our orbit, for Jupiter's orbit, based on the size that we're getting from Betelgeuse itself. When we're looking at stars, even through the Hubble, we're not usually getting a lot of detail from the stars. They are still sort of blobs of light in Roy G. Biv. So when you're going to an observatory and they're telling you we're looking at this star or that star, prepare to be unimpressed, because when you're just sort of looking at it through a regular telescope, you're going to get a larger point of light, but basically for stars, you're going to get a point of light. and even with the Hubble, we're getting a little bit of an enhanced point of light. This again will be time lapse, so this would not be what you would see when you're sort of looking through it through your eyepiece. When stars begin to leave the main sequence, they will come off to the right. They'll come up sort of up and to the right. And that happens when they have exhausted their primary hydrogen supply in the center. And you can sort of see how many years it tends to take these as well. Remember in our protostars, they start out here in sequence, they drop onto the main sequence, then they float back out here again. And this is where they begin to change color, because notice the surface temperature drops and drops and drops as they expand. So we can have really large stars that are reddish because their surface temperature has dropped, but they started out in this blue hot zone over here. So Betelgeuse used to be a big blue star. Now it's a big red star. Most stars occur in clusters, and we have two different types of clusters. We have open clusters, Pleiades here, and globular clusters, which is this one here. They can be a few dozen, a few hundred, a few thousand, sort of loose collections of stars. Quite frequently, they formed from the same nebula, and quite frequently they are interacting gravitationally, but they're not really holding on for dear life gravitationally along the way. The Pleiades here are recently formed, haven't even blown all their gas and dust away, and we can see that particularly like in this lower center star here, or this upper sort of center to the right star here. This is one of the few things you can see with the naked eye at night when you've got the right viewing conditions, where you can actually see the fuzzy patch of gas and dust around it. So it's rather interesting. Globular clusters are in fact holding everyone together gravitationally. Typically, there is not a black hole at the center of globular clusters that's acting as the main gravitational, if I can use the word magnet. It's not magnetic energy that's holding things together, but you get the concept there. It's actually a mutual gravitational hold on things. One of the things you might notice immediately, what's the color difference here and here? What do you think the energy difference? Blue is high energy, red is low energy. What do we know about blue stars and how long they live? These won't live all that long. What do we know about red stars and how long they live? Well, unless they're sort of on their way out, the yellow and red stars tend to last a very long time. Globular clusters are some of the oldest things in our galaxy. In fact, they may predate the spiral structure of our galaxy along the way. This is Omega Centauri. When we're looking at it here, we can sort of see just sort of how densely packed it is. We can also see essentially the coloration that's there is in the Roy area. Mostly yellow, mostly sort of white kind of color, a little bit of red and orange that's in there, a little bit of smattering of blue. When we look at it in sort of different wavelengths here, we're sort of adjusting our time exposure and a little bit of the way that we're looking at it here. We're looking at the center in B of this here, and we can see there are quite a number of blue stars. The blue stars are ones that are large enough to burn out their hydrogen into helium, but still have enough material left over to push down and ignite the helium. Again, I'm using that term ignite loosely, into its own fusion reaction into higher elements along the way. But notice the predominant stars in these are not the blue stars. When we looked at stellar populations a few chapters ago, remember for every blue star there are quite a number of medium-sized stars, sorry if I could speak that would be helpful, and lots of smaller stars. So that kind of population distribution is not unusual for us. Here we have an open cluster that's called the Jewel Box. NGC stands for New General Catalog. We have different catalogs in the history of astronomy that overlap with each other, and we tend to historically keep the same designations as much as we can of earlier catalogs, so we're not always reinventing the wheel. But you'll often see, say you go to a Wikipedia page for a star, you'll often see sort of this number, this number, this number, this number. That's because those are all the different catalog numbers for the different stars or the different objects. This one here, as we can sort of see, has very pretty stars. It has some white stars, some blue stars, the interesting sort of amber star there in the middle there. So these are not going to last all that long because they are big blue stars, which means they'll burn themselves out rather quickly. So when we're sort of looking at different kinds of clusters of stars, that helps us to work on the ages of stars along the way. So when we plot a cluster on the HR diagram, we're going to often see a distribution something like this, where we'll have some stars beginning to burn themselves out before other stars have actually made it all the way down onto the chart here. Here's another young cluster. Again, a new general catalog number, 2,500 years or 2,500 light years away from us. And it's called the Christmas tree cluster, still relatively new because it's got a lot of gas and dust that's still there and a lot of red gas and dust, which means that hasn't been heated up too much. That's going to be an area of lower energy. Then we can sort of see this plotting here. Notice that the things here tend to be more towards the bottom, where this is a lower energy overall kind of thing, whereas these have a lot more towards the top, and that makes sense when we're looking at those. So here again, we have yet another NGC. Most of the massive stars in the center will begin to explode and return their gas and dust to the nebula before the rest of this nebula around it will become stars itself. So we have multiple things happening. It's almost like a forest. You will see trees that are dropping over because they're old and have lived their lifespan in the midst of other trees growing and in the midst of seedlets beginning to just sprout and put out their first leaves. That happens in the universe as well in nebulae such as this. Here we have a cluster M41. Again, M is one of our oldest, most respected catalogs. Doesn't have very many objects in it. This was done by a guy named Messier. I believe I talked about him before. This one is an older cluster. Notice several stars are starting to leave the main sequence. They've exhausted their hydrogen fuel supply. And we've got quite a number up here where we're in the instability strip area, which we've talked about before with regards to Polaris and some other stars along the way. Note that there are a lot of orange kind of colorations here. Those are on their way to becoming red giants, like Betelgeuse. So as we post onto the HR diagram different kinds of our clusters, look at the Pleiades here in particular with our triangles. Notice there are quite a number of them in the what we would call regular zone, but those big ones are already beginning to have burned themselves out. Those are those big blue stars that we see with the naked eye. Here's sort of an updated one with just the Pleiades. We can see where these are beginning to turn off. We call this the turnoff point along the way. And it makes sense that the ones that are higher up here burn themselves out faster. So they're getting to the turnoff point. They are leaving the hydrogen into helium point. So some of these larger stars aren't going to last even 100 million years. Again, think about our star lasting 10 billion years or more. That means we're going to last 100 times longer than these stars that are here along the way. Some of the stars in the Pleiades, however, are going to last a very long time, but we don't recognize them as being the main stars in the Pleiades. It will cease to look like the Pleiades by the time these larger stars burn themselves out. We can see a couple of other clusters that are depicted here, including this one at the top here, where we have in the constellation Perseus, where quite a number of them are huge and have turned off and are now over. This is the point where we're in the top upper right corner where they are about to blow. So that's a one to watch as well. When we look at globular clusters, they tend to have many, many more smaller stars. They last a very long time, but again, they've been around for a long time. So most of your stars last 10 billion years and you're 10 billion years old, then a lot of your stars are turning off. Our sun would be a typical star in most globular clusters. Notice we've got these things down here. This is the zombies zone. These are the white dwarfs. These are the leftovers from that along the way. So here we again see an older cluster that is sort of turning off many, many more smaller stars. And as they turn off here, some of the larger mass stars will make it up into this range. They'll never quite make it up into the complete upper right-hand corner. This is where supernova explosions happen. This area here, we have other things happen, and we will see what happens along the way, which includes what's behind me here, Planetary Nebula. Here's another depiction of another cluster. You notice something from all of these. They're all going in the sort of same direction. They all have a similar pattern. I won't say the same pattern, but they typically have similar patterns, although some of them are adjusted higher, some of them are adjusted lower, depending upon the overall sizes of the stars in the clusters along the way. So we can see a sort of a brand new cluster where everything is newborn and they're all in the main sequence zone. They're all burning hydrogen into helium, happy, happy, happy. But of course, the larger ones will begin to turn off sooner. The smaller ones will begin to turn off later. So we might see this turn-off point gradually go down and down and down and down through any particular cluster as it happens. And I believe I've shown you this chart before. Again, for every major star that's out there, we have a smattering of what we would still consider to be big stars, but not supergiant stars. We have a large collection of medium-sized stars and a huge grouping of small stars along the way. Our sun would be sort of right in this line here, sort of just inside. We're not a dwarf, we're not a red dwarf, we're not a brown dwarf, but we are what we would probably consider ourselves to be a yellow dwarf. That tends to be a fairly typical description of our sun as a yellow dwarf star. So a star like our sun will be 5,000 to 6,000 degrees surface temperature. It'll be somewhere on the main sequence, sort of towards the middle, but edging towards the lower end towards the middle. And when it turns off, it will go into this direction. It'll never reach the supernova stage. And we'll talk about why later, but it will sort of go back and forth. It will go into that instability thing. So we will have different processes that happen. It will try at some point to begin to fuse the helium, and we'll have what's called a helium flash. And we might even have just enough for a little bit of the helium to fuse into carbon and oxygen and a few other things, but that won't last very long. So when we have a low mass star, these will be the sequence. We'll have the protostar, remember our jets of energy and our protoplanetary disk that's around. It becomes a regular main sequence star, usually low mass, which means it's going to be a red dwarf or a yellow dwarf kind of thing. It will turn into a red giant. Notice it's not a red supergiant. It doesn't like take over the whole page here. But as it begins to run out of hydrogen, it will then sort of recollapse as it tries to fuse the helium. We call that the helium burning phase. Then what we'll have inside is some of the hydrogen that wasn't used up will begin to fuse, as well as helium that will begin to fuse, and we'll have a buildup of carbon and other kinds of things that will happen. But this becomes very unstable, and as this happens, it begins to shed its outer layers, turning into a planetary nebula. which is what the ultimate fate of our sun will be. What's left over in the center is the sort of the white hot core. We call that a white dwarf. And a white dwarf is actually, in terms of size, not much larger, volume-wise, than the Earth. However, density-wise, in terms of how much material there is, if I had a sort of a sand bucket full of material from a white dwarf, say it was cool enough to do that, not incinerate everything at all, probably weigh as much as Mount Everest, maybe all the way up to as much as the entire Himalayas, just in that one bucket, because everything is so compressed. And it's not actually now burning anything. It's not generating any energy as much as it's just leftover energy from the core. Think about your car being shut off, but the engine's still hot. And it's going to be hot until all of the heat dissipates away. That's the same principle that's happening here to a large extent. Inside, we're going to have our hydrogen and helium. What we're going to see is we still have hydrogen, we still have helium, we have areas where it will continue to burn a bit. We're trying to burn some of the hydrogen that's still there, but it's not happening in the core anymore, so we call that shell fusion. We're trying to burn some of the helium, but that's not really working all that well, particularly as the ashes left over from the helium fusion, carbon and oxygen, interferes with that, sort of changes things inside, and it just makes it unstable. And what we get can be truly, truly fabulous. So I'm going to let you read the material that's down here, which helps describe all of these different images on your own. But what happens as a lower mass star like our sun begins to shed its material, these are planetary nebulae, and the 1A here is what you're seeing behind me in a different perspective as well. The ring nebula, again, M, our Messier catalog, M57. And one of the things that we can sort of see, one of the interesting things is this is sort of a sky inside out. So when you go outside right now, if it weren't raining, you could look outside and the sky would be blue. But during the morning, the sky is in the Roy area, sort of red and orange and maybe a little bit of yellow. Then it's in the Biv area, but then back in the sunset area, we get back to Roy. That's what's happening here. We have our middle of the day, we have our sunrise and sunset, but it's all the way around. And the neat thing about this is, if I were looking at it this way, blue would be in the middle with all the Roy stuff around, so sunrise and sunset. But if I were looking at it that way, the blue would still be in the middle. That's because of the way the light works. It's truly interesting. When we've got other gases and dust that are occurring in these, or we have other kinds of sort of gyrations or gravitational pulls or different kinds of starquakes and explosions, it can change the dynamics of how these planetary nebulae happen. And so we get quite a number of different kinds of structures that come off of this along the way. So we can still tell where there's higher energy and lower energy areas. They're called planetary nebulae not because they are planets, not because they even have planets. That's a leftover mistake from the history of astronomy, where when people were looking at them with low power telescopes, they thought they might have been seeing planets. And one of the reasons why Messier put together his catalog was people kept rediscovering the same thing. It's like, oh, look what I've discovered, a new planet. And he's like, 50 people have discovered that before. Don't waste our time. And so he put together this, but they began to call them planetary nebulae. Confusing a little bit because it's not planetary. But from the old style telescope view, they would look like that. One of the things that we might see when we are looking at the different ways in which these things happen is we can see energy around the star. We have the star itself with magnetic fields, with solar wind, stellar wind. We have a solar wind that hits our planet and creates the aurora, the northern lights that you can see in Upper Peninsula of Michigan or Canada or Iceland. That's one of the things I always look for when I go to Iceland. Can be quite interesting and spooky. But there are different ways in which these kinds of energy pieces can work, depending upon the dynamics of the star itself. So as we're sort of looking at the different planetary nebulae, again, it depends on which way we're looking at it as to what we might actually end up seeing. And quite frequently, stars, and Jupiter actually does this as well, has a big gravitational torus, which is an energy area, sort of electromagnetic generated energy that can really interfere with the gas and dust along the way. So here we have, again, Eta Carinae. This whole area of hot gases, we can see super hot in the sort of middle here because we're getting a bluer kind of thing. We've got lower energy areas as it goes more towards the Roy, towards the reddish area here, but we've got two large lobes that are coming out, which give us an indication of the dynamics of things that are happening in the center there. So it says it appears blue-white because it contains dust and reflects the light of Eta Carinae. And of course, that gives us a clue as to just how bright this star is. It is truly, truly a spectacular thing that is happening here. So one of the things that we're seeing here is this is a star that is so large that it is unstable and generating these kinds of effects. Here, again, we have our hydrogen and helium gases, white dwarf in the middle, which is the leftover core. Sometimes we have some starquakes and other things that happen. This one is sometimes called the skull. You can see why that's there. This one is similar to the one that I've got behind me, but you can see there's a sort of a gentle fragmentation that's happening here, but the same Roy G. Biv effect is happening as we look at it. And then here, this is sometimes called the eye. And this either is happening from stuff that's happening on the star in interesting ways, or it might have a companion that's going around it that is causing this kind of spirograph thing. But again, we're having the Roy G. Biv effect with the Biv in the middle and the Roy on the edges along the way. So planetary nebulae can actually end up being some of the most beautiful things that are out there. Our sun will turn into that. It would be a good day to be on a nearby star watching from afar when it happens. Here we are right now, sort of roughly 5 billion years into the lifespan of our sun. We've got another 5, 6, 7 billion years to go before we begin to leave the main sequence, because we've run out of enough hydrogen to keep the core going, and we've built up enough helium in the center that it's interfering, it's sort of gumming up the hydrogen works. Notice what's happening here. Our sun will get more luminous and will brighten over that course of time too, which means, if you remember from our last lecture when we talked about the habitable zone, the habitable zone will go out further and further and further. By the time we're up to this level, 5, 6 billion years from now, the Earth may be too close to the actual sun to be habitable anymore. It will be too hot, the water will have all boiled away. Again, a good time to be on Mars, a good time to be somewhere else. By the time we're up to here, where we have that helium flash, the instability inside is trying to retool itself, and we get this big flash, that will be a good time to be outside of the solar system. We'll have a brief period, millions of years, but still not billions of years, where we settle back down, still much larger and much brighter than we are today. I mean, by this point, Pluto would be a balmy place to be, most likely. And then as that runs out, we're going to have the sort of the ejection of the material into a planetary nebula. One thing to keep in mind, when we reach the helium flash stage, the sun will have expanded out to about where the Earth is now, which means the habitable zone will be way, way out by that point. But then the habitable zone will shrink back in. So we're not going to find any planet in our solar system that's going to sort of be the one size fits all for us to go to there. So again, it'll be a good day to be around Proxima Centauri. If there's a good planet around that, it'll last a lot longer. And it may be also a good time to be around some other star. Sirius is not an option because it will be long gone. Sirius will be gone by the time we reach here, because it's twice the size of the sun in terms of mass, which means it will last a lot less time. When we look for new stars to go have new homes around, pretty much want to look for the smaller stars that are going to last a long time. But yep, this is the fate of our star. When we're dealing with high mass stars, our blue giants turn into red supergiants. They collapse back down when they're sort of recalibrating. But one of the things that happens inside there is that they do have enough mass to take that carbon oxygen core and begin to burn it and have more and more and more shells. So you'll have different types of fusion that are happening inside. That becomes incredibly unstable, and that's when we have big explosions. And the explosions just sort of out, not some gentle sort of puffiness like we have in our planetary nebula here. These are huge, huge events, and this is what Betelgeuse will do. What's left over behind there is a neutron star. Neutron star may be, in terms of volume, about the size of Bloomington, maybe the size of Indianapolis, probably smaller than that along the way. But again, one sand bucket full of material from the neutron star might weigh about as much as the North American continent. It's going to be really, really dense. Yeah, use that stuff for weightlifting because it'll help. Look inside that kind of star. Again, we have our hydrogen and our helium, but notice we've got oxygen and carbon and magnesium and neon and silicon and sulfur and all sorts of things until we get iron. Iron at the center. Iron doesn't fuse. Well, I'll take that back. Iron fuses, but it only fuses when you add energy into it. See, all of these other processes here, and when we're converting matter into energy, we can use E equals mc squared. Hydrogen into helium, helium into carbon, on and on and on and on, all the way up to iron. Every time that happens, they generate energy by it happening. When iron fuses, it takes energy away. So in other words, it's not going to help the star shine anymore, it's going to shut the star off. And that's when it explodes. So you remember the periodic table of elements, that big sort of chart where you have the H in one corner, helium, He in the other corner, and all the other boxes with the 92 naturally occurring elements and the other ones that we have created in our own technological ways. After that, not too many of them. All the way up to iron, those things are created inside of stars, can be created inside of stars. From iron further, those things are created when the star explodes. That's why there's not a lot of that stuff. There's not a lot of zinc. There's not a lot of gold. There's not a lot of stuff like that out there along the way. We will talk more specifically about that in our next chapter because we're going to look at the death of stars, and that's where it begins to get really interesting. And I'll see if I can find I'll see if I can find the CNO sort of cycle. I showed you the proton-proton chain where we get from hydrogen to helium. There's another cycle that the larger stars do where we build the elements that are higher and higher and higher from there. So I'll see if I can get that up there for you. And otherwise, stay tuned.